probability of 0.01. It maps to a weight, pi of 0.01, that is greater than 0.01. So that's the overweighting of small probabilities. Yeah? And it looks like, and that has to be, that's because the slope is greater than 1 at first. And it looks like they think that's going to continue to be true, up to some, I don't know, 20, 30%, somewhere in there. And then it's going to start to flatten out. But let's go up here. Let's have this be probability of 1. I apologize for things getting squeezed in there. I didn't put that p there, so I'm kind of stuck with it. But let's have this be 0.99. So here's that last percentage point of probability. Okay. What this is saying, and this seems like a pretty good starting place if you're trying to make the math work, is that the weight that people put on a probability of 1 is equal to 1. In some sense, we're just sort of normalizing the weighting function so that we can work with it mathematically. But let's just roll with that for now. It could be something else. It wouldn't change the outcome. It just makes the math simpler. What this function is telling us is that if we take away 1%, what we get is that the probability, that the weight that people assign to 0.99 is less than, right? 0.99 would be there, so that weight must be less than 0.99. Yeah? And what that means is that the difference between the weight they put on a probability of 1 and the weight that they put on a probability of 0.99 is greater than 0.01. Okay? So they're overweighting small changes in probability both at the bottom and the top of the scale. That's what that function tells us. So that captures the overweighting small probabilities and the certainty effect. And this shape with that inflection point there, which is somewhere around a third, I don't remember exactly where that's estimated to be, but that's actually been estimated by an extremely mathematically proficient behavioral economist named Dražen Prelic, who I assume is from somewhere in the Balkans. Yeah. Sorry, a little bit louder. Oh, I'm sorry, that should have been a less than. Thank you for catching that. That should be a less than. Yeah, the weight that people put on 0.99 is less than 0.99. What that means is that the difference between the two, the difference between certainty and 1% less than certainty, is greater than 0.01. Thank you very much for catching that. Okay. So that's what we think is going on with the probability weighting function. And basically, keep in mind, I don't think I actually pointed this out, Kahneman and Tversky have preserved a huge chunk of expected utility because they have preserved the idea that people sort of evaluate gambles according to some linear combination of sort of, what do we have, sort of P, A, X, A, right, et cetera. They've preserved this linear combination idea of how people feel about gambles, that they just weight the probability and place a value on the outcome and then add up those weighted bits. Who knows how, right? If we actually were to crank up some kind of automatic, some kind of artificial intelligence computer model of how people feel about their about different risky choices, we might come up with something completely different mathematically, right? It might be that they take the sign of the probability and raise it to the power of some crazy value and then put all those into a dish and pull one out at random. I mean, who knows? So they preserved a huge important chunk of expected utility for good reasons. Well, I tried to convince you last time that evaluating outcomes and then weighting them by probabilities was at least more psychologically realistic than trying to average the outcomes and then see how you feel about that. But we don't really know whether this linear combination approach is right. I will tell you this: it's wildly more mathematically trackable than anything else. So unless we really find it completely unhelpful, it's not a bad thing to stick with. Right? Mathematical tractability is worth a lot in economics. So if we take this value function that I have on the board here and stick it in here, and this probability weighting function that I have up here on the screen and stick it in here, that's prospect theory. And it earned Danny Kahneman a Nobel Prize, rightly, I think, and it explains a lot of things. And it's a really very powerful piece of behavioral economics. So I'll talk a little bit about what it explains in a few minutes. But first, I want to backtrack. So far, all we've been doing is talking about positive economics and seeing how that very specific and carefully designed violations of the predictions of expected utility theory can point us towards sort of a more psychologically realistic correction of the standard model. Now I'm going to drag you through a little bit of some of what this does normatively. Okay, not quite as much emphasis on this as in past lectures. So the independence axiom is, if you were to go and dredge up von Neumann and Morgenstern's book from 1944, in which they actually presented their theory of expected utility, you would discover, or indeed, if you go and get a PhD in economics, in the first few weeks of your advanced micro theory class, you will be told that the independence axiom is overwhelmingly the most important assumption in von Neumann and Morgenstern's expected utility theory. Daniel Bernoulli in 1738 didn't know anything about the independence axiom. So what it says is roughly, the actual mathematical statement of it is more complicated than this, but roughly what it says is that if you add an identical outcome to two gambles, it should not change people's preferences over those gambles. So if you're choosing between one gamble, which is with 50% probability it will rain and I won't have an umbrella, with 50% probability it won't rain, but hey, I didn't have to carry my umbrella, and another gamble which is with 50% probability it will rain, but I've got my umbrella, and with 50% probability it won't rain, but I don't with 50% probability it won't rain and I'm carrying around an umbrella, but with 50% probability it'll rain and I don't care, so I got it right. If you're trying to choose between those two gambles, and someone comes along and says, well, what if I add into each of them a 10% chance that the Red Sox will win the World Series, right? It shouldn't matter how you feel about carrying an umbrella. It shouldn't affect how you feel about carrying an umbrella on a day when there's a high chance of rain. That's the sort of like dumbed-down extreme case to explain roughly what the independence axiom means. In the paper that you're assigned to read, Kahneman and Tversky, for reasons I don't know, call this the substitution axiom. Okay? So that's where you'll find it in the paper. Now, it turns out that if you this isn't the only assumption that von Neumann and Morgenstern make about risk preferences, but it's the important one. It turns out that if risk preferences satisfy this axiom, if people consistently make choices over different gambles that satisfy this axiom, and that actually really people are indifferent to what are called irrelevant alternatives, if people's preferences are independent of irrelevant alternatives, then it will be the case mathematically that their preferences can be represented by expected utility theory. Okay? So this is the critical assumption about preferences that makes the model, that makes the model the right model. Okay? And so, for example, what this is parallel to is when we were studying Hicksian utility theory, and when you studied it last year, it's the rationality assumption that people's preferences are complete and transitive that makes the model mathematically correct. If your preferences satisfy rationality, then they mathematically can be represented by a utility function. And it does not matter that you don't actually have a utility function in your head. I can write down a utility function. If your preferences are rational, I can write down a function. It will represent your preferences. Okay? Likewise, if your preferences over Gamble's satisfy the independence axiom, then I can write down an expected utility model. I can write down some v of x and use linear probability weighting, and I will be able to represent your preferences over Gamble's. So this is one of these things that I like to point out to people. When we say under these assumptions the following is true, we don't mean we think that these assumptions are correct and we think this is the way the world works. We mean we've written down a mathematical model in which we have precisely captured these assumptions, and it is a mathematical fact that if those assumptions hold, then our conclusions are correct. Okay? It's not a supposition, it's a mathematical fact. That is why von Neumann, well, that and the fact that they invented game theory is why von Neumann and Morgenstern are famous. Okay? Now it's interesting. I don't know much about either of them. Morgenstern was a mathematician; he wasn't an economist. So, and John Nash, who also contributed at this time to these theories, was also a mathematician, not an economist. So it's interesting that sort of like we're sort of dealing with a comparison between the standard model, which was sort of like math and economics, right, with the behavioral model, which is psychology and economics. But that's what they did, and it's brilliant, I think, unarguably. But it's also wrong. So let's take another look at problems 3 and 4. We used them a minute ago to get some insight into this probability weighting function and the certainty effect. But let's take another look at them. Okay? Another way that I could represent these problems. Here's problem 3. You're choosing between a 0.8 chance of $4,000 and a 0.2 chance of 0 on the one hand, or another gamble, which is sort of what's referred to as a degenerate lottery, where with probability 1 you get 3,000. And what we find is that in problem 3, 3,000 wins. Right? Now, what if I were to frame things a little differently? What if I were to say to people, okay, the lottery over here on the left is going to be a little bit different. It's going to be set up a little bit differently. First, we're going to subject you to an initial lottery in which, with probability 0.25, you'll get the 80-20 lottery, and with probability 0.75, you just get nothing. You'll walk away. Okay, so I'm giving you a 25% chance to even face the 80-20 lottery in the first place, and a 75% chance that you just, you leave my booth and go on to the sports card trade show. And let me transform this degenerate lottery over here in exactly the same way. With probability 0.25, you get $3,000 for sure, and with probability 0.75, you get nothing. Okay? What I've done is exactly what the independence axiom is looking for, which is that I've added an identical arm to these two lotteries. Right? I've added this 75% chance you just get nothing, and then 25% gets weighted onto whatever you were faced with before. Okay? So now, I don't know if you're catching this, but this is now problem 4. Okay? In terms of outcomes and probabilities, this is now problem 4. Because what this is saying is, if I just write this out, again, if I assume linear probability weighting, what I get is this gamble is 0.75. Hang on. What I want to do is I want to say the utility of this gamble is equal to 0.75 times v of 0 plus 0.05. Right? So 0.75 times v of 0 is this part. And then you get a 25% chance of a 20% chance of 0. So that's adding in an extra 5% chance of 0, right? So it's that plus 0.05 times v of 0. Plus you get a 25% chance of getting an 80% chance of 4,000. So overall, that's a 0.2, a 20% chance of winding up with v of 4,000. And then, of course, we just add these two things together. And that's problem 4, right? You have a 0.8 chance of getting 4,000 and a 0.2, sorry, 0.8. Is that right? Yeah, you have a 0.8 chance of getting nothing and a 0.2 chance of getting 4,000. And this thing, by the same logic, becomes 0.75. The utility of this gamble is equal to 0.75 times v of 0 plus 0.25 times v of 3,000. That's now problem 4. If expected utility theory is correct, and by the way, this does not hinge upon what we believe about the value function. It only hinges upon the linearity of the probability weighting function. If that's the case, then I ought to be able to just do some simple math. And the first thing is I ought to be able to just discard that 75% chance of 0 from both sides. Mathematically, right? I should be able to just write down 0.05 times v of 0 plus 0.2 times v of 4,000. Better still, so what problem 4 said was that people like this thing better, right? So they better still like it when I've taken away that 0.75. So that better mathematically still be greater than 0.25 times v of 3,000. And then I ought to be able to just multiply both sides by, what am I multiplying them by here? 4, right? I ought to be able to just multiply, so this would subtract 0.75 times v of 0, and now I'm just going to multiply by 4, and I should get 0.2 times v of 0 plus 0.8 v of 4,000 is greater than v of 3,000. Okay? If you pick it apart, it's the same math as what I did 2 slides ago. But I've set it up in a different way to demonstrate really explicitly that adding in this 75% chance of getting 0 before you actually get to problem 3, which turns it mathematically into problem 4, changes people's preferences. And that's a violation of the independence axiom of expected utility theory. So in other words, do you mean that the utility, the little instantaneous utility function actually isn't constant? It changes? So I'm not following your question precisely, and I'd be happy to talk about it in greater detail, but my hunch is that the answer is going to have something to do with the fact that you just said specifically that those variables aren't independent, right? So there's some violation of independence, which is what the independence axiom is all about. So let's talk afterwards to figure out exactly how or if that intuition is right or wrong with respect to what you're bringing up. But under the assumptions of expected utility theory, this can't happen. There could be some other explanation for it besides the overweighting of small probabilities, but whatever that explanation is, it still violates expected utility theory. It's still a violation of the independence axiom. Okay? So the independence axiom, now notice, okay? This proves that the LA paradox proves that the independence axiom does not hold in this situation. Incidentally, it also violates the basic rationality of preferences. Because rationality of preferences says that if you prefer one apple to one orange under certain circumstances, you should continue to prefer one apple to one orange. Right? Your rationality says you should have a consistent ranking for different outcomes. And what we've got here is a preference reversal. You went from preferring this to that under problem 3 to preferring that over this in problem 4. Okay? That's a violation of rationality. It's not just a violation of the independence axiom, which is this like really advanced extension of rationality that we stuck into expected utility here. It generates a preference reversal, which is a violation of the most fundamental building block of neoclassical economics, which is the rationality assumption. Okay, so trouble in paradise, but it's trouble we're used to by now. Okay, this is now the beginning of today's lecture. And so today's lecture is entitled Applications of Prospect Theory. And by applications, what I mean is situations in the real world that prospect theory does a better job of explaining than the standard model. Okay. So the first one is a thing called the equity premium puzzle. Where's my B-school person? I know there's at least one person who's come across this, because we have somebody in the class from the business school. But the equity premium puzzle goes like this. So very roughly speaking, we can think about two different types of investment. An equity investment, for example, buying stock in a firm, means that you become part owner of the thing, of something. Usually it's a firm, but sometimes it's so you could become part owner of a racehorse, blah, 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 blah. If the firm does well, you do well. If the firm does badly, you do badly. That's a risky investment. or debt. For example, bonds. You could buy bonds from a company or from the government, or you could actually just make a loan to a firm. Okay? If the firm does well, you get your principal plus interest. If the firm does badly, you get your principal plus interest. Right? So this is risky, and this is risk-less, roughly. Average annual return on investments from 1889 through 1978. It does not matter if you continue this to the present. It doesn't even matter if you begin the series right before the massive meltdown down in 1929. Average annual return on investments over the years has been 7% on equity and 1% on debt. Okay? Which means that there is a premium on equity of 6 percentage points, roughly speaking. What do I mean by a premium on equity? What I mean is you get a premium, you get a bonus, you get extra payoff if you're willing to take the extra risk. But another way of putting that is people demand a higher return for taking on that risk because they don't like it. Okay? They need to be compensated for taking that risk because they don't like the risk. And they're willing to accept a really quite dramatically lower payoff in exchange for having that risk taken away from them. Okay? Now, back in 1985, this got labeled a puzzle by Mera and Prescott because what they did was they took a really quite flexible version of expected utility theory and they tried to find out how risk-averse people would have to be under that model in order to generate an equity premium of 6 percentage points. And what they found was that people would have to have a coefficient of relative risk aversion of 30. So let me just explain what that means. I don't know if this is, I can't remember if this is in 100A or not. I have a feeling that it may not be. The coefficient of relative risk aversion, okay, in expected utility theory, if I assume that you've got some instantaneous utility function, little u of x, I want to have some sense of how concave it is, how risk averse you are, right? How curvy is it? So this coefficient is negative x times the second derivative of the utility function evaluated at x divided by the first derivative of the instantaneous utility function evaluated at x. So it could be different depending upon how much wealth you have, right? But starting at a certain point, whether you have wealth of 5,000 or 10 million, we go to that point on the little u function, and we figure out, we plug in x and the first and second derivatives of the utility function evaluated at x, and we get this coefficient of relative risk aversion. Okay? That number has got to be 30 on average for investors in the New York Stock Exchange to explain a risk premium of 6 percentage points. Now, what does that mean? Suppose, or not, yeah, one of the things that economists always like to ask is that a big number or a little number? Suppose that u of x is equal to the natural log of x. Okay? Which means that the first derivative of the instantaneous utility function is 1 over x, and the second derivative is negative 1 over x squared. That means that under log utility, this coefficient of relative risk aversion is equal to negative x times negative 1 over x squared divided by x, which equals 1. Okay? So log utility has constant relative risk aversion, and it has it's unit risk aversion. Okay? Now on your problem set, you're going to be working with this utility function quite a bit, because we've assumed prospect theory